The next speaker is Hameister. He will talk about the Hitchin systems for symmetric pairs. And also remember about the dinner. If you want to go for dinner, please sign up this morning.
Awesome. I just want to start by thanking the organizers for putting this conference together, and also a special thanks to Oscar and the I don't know if she's here now, but Anna for they had talked to me in the early stages of the project, and I think they gave me some broad contour of like some of the structures to expect. So thank you for that. So I just want to set some notation first. So I'm in this. G is going to be some reductive group. It's going to be over some algebraically closed field, K. And I'm going to assume that the characteristic of K is either 0 or P positive for P good for G. If you are unfamiliar with the technical assumption of being like good for G, you can just think greater than a Cox-Zerr number, and that'll be fine. Also, I'm going to need to add one kind of technical condition, which I'm not going to say now. It's going to be a condition on kind of what will be the restricted root system, but I can mention this later. A very mild condition. So let's fix some involution. So this is going to be some algebraic involution. If you're working over C, this is going to be holomorphic. An algebraic group involution, I should say, respecting the group structure. And this involution is going to help us define a few pieces of data. For one thing, it will define group K, which will be the fixed points. But this might have some components involved. I'm going to take a connected component. And it will also define some Cartan decomposition on the Lie algebra of G into a +1 and -1 eigenspaces. So eigenspaces of the theta action. And the main kind of objects that I'm going to consider are called symmetric pairs. And this is going to be this group with involution together with some subgroup H, where H sits between K and the normalizer group of K in G. The usual definition of symmetric variety keeps this kind of fixed between some fixed points. There will be a step later in which I have to do some inductive procedure. So it is necessary to kind of pass to this normalizer, but it doesn't change too much. Okay, and kind of one observation is that H acts on this frac P by the adjoint action. So let me give a few examples of these sorts of things. So maybe example 1, I'll refer to this as the diagonal case. This was the case of G is product of 2 reductive groups for G1 reductive. My involution swaps factors. And then my H I will take to just be K will be my G1 embedding inside of this product diagonally. And my frac P is kind of this anti-diagonally embedded copy of frac G1. And the action of H on P in this case recovers the adjoint action. So this G1 action on frac G1 is the usual adjoint action. And kind of so this kind of recovers the Hitchin systems in the Lie algebra case. And I have another motivating example here. This is I'll refer to as kind of the GLN cross GLN inside of GL2N case. If you are familiar with kind of real forms, this is related to what's called the UNN kind of real form. And if this has my involution on kind of a 2n on some n by n blocks is given by negating these off diagonals. So I have some frac P, which is kind of my off diagonal parts. And I have my H, which I'll take to be K, to be kind of this block diagonal copies of GLN cross GLN. So think of this block diagonal inside of this GL2N. Okay, and kind of the principal object of study is this map from the stack quotient of P mod H to this GIT quotient, where if you recall, this is the spec of the invariance ring of H acting on P. And I want to study this kind of in the philosophy that that Noah introduced kind of yesterday, which is that I'm going to first introduce some regular locus here, and then we'll see kind of the appearance of some extra regular quotient pop up. So first, let me just recall. I'm going to take IH inside of H cross P to be my centralizer group scheme. And I'm going to say that a element of P is regular if the dimension of IHX is minimal. And note that this definition of regular has to do with the H action. So a word of caution is that the regular locus in P does not have to agree with the regular locus in G in general. This is what's known as the quasi-split condition. Now, I'm not going to assume that for this first part of this talk. However, I will say in the two examples that I wrote down, it is the case that that these two regular loci do agree. So you can think about it as just the intersection of usual regular elements in these examples. Okay, so the first problem that kind of arises here, and again, this is a bit of a review from yesterday, is that this this stack, when I restrict to this regular locus, mapping to as GIT quotient, this is not a gerb. And in less fancy language, it just means that if I fix a closed orbit here, there's not necessarily a unique regular orbit lying over it. So for example, if I take the n=1 case of that second example over there, so if I take this GM cross GM sitting inside of GL2, then this action of so the action of GM cross GM acting on my space P, which in this case is just this off diagonal copies. So this is going to be this copy of A2. Is a hyperbolic action. So if I multiply by, let me just write these coordinates as BC, then this is going to just multiply x over y on B and y over x on C, And the orbits of this action I can draw as kind of hyperbolas inside of A2. And you see over the origin that there are 3 orbits over 0. there's kind of the
zero and what?
I guess over the zero on the GIT. So yeah, I'm trying to say yes. So there will be kind of three orbits kind of lying over these coordinate axes. So one will be the closed orbit. And then I will have two regular orbits given by each of the coordinate axes. So I have one regular orbit here, the closed orbit here, and then another regular orbit here. So this kind of gives us a nice concrete picture of this intermediate space. So I have sort of this P-reg stack quotient H mapping to this fat slash quotient mapping to this GIT. And I'm gonna so this intermediate space, what this will be is the so this will parameterize kind of the regular, this will be the orbit space of kind of the regular or this will be the H orbits of the regular H orbits, sorry. So one way to say this is that it's the rigidification of the stack P-reg quotient H by regular centralizers. So I remove the regular centralizers and I get actually in this case an algebraic space. So in this sort of symmetric pair case, this will always be some algebraic space. I'll discuss this a bit. And in our example, this thing is looking like some affine line with doubled origin. And this is looking like some copy of A1. And this is collapsing kind of my two regular orbits to the closed orbit in their closure. Okay, so I want to state kind of the main result here that I'll talk about on this intermediate space. And then my plan was to discuss its proof and then try to draw some consequences, at least in the examples that I've written. So the main result here is that so if I have some symmetric pair which is simple, and this means that G is simple, then then unless it's one particular bad one, so unless this is unless G theta H is one particular form SO4n, theta is conjugation by identity 2n minus identity 2n, and I get SO2 cross SO2 or SO2n cross SO2n. So unless it's this form, there exists some divisor, which I'll call DNS, inside of the GIT quotient. So a divisor such that my regular quotient, or my regular quotient is equal to gluing of two copies of the GIT over the complement of this divisor. And moreover, so moreover, what I'm going to describe is we can compute this divisor So there's a nice way of figuring out what this divisor is. We can reduce to the simple case. And for the purpose of this talk, I will not discuss this third part, but this last form, this the special form can also be described. It's a little bit more technical, but the ideas are basically all there, just computationally a little bit more intensive.
Is it just gluing more copies?
So say
Is it just gluing more copies? Or is it more?
it's right. So because you glue kind of you glue 4 copies instead of 2 copies, it becomes a little more computational because you have to figure out how do they glue, not just do they glue. Right.
But-
Any other question? Yeah.
But is it 4 copies also glued outside of divisors?
So you have some gluing that happens in codimension 2, 4 degenerating to 2, and then those 2 degenerate to 1. But kind of the degeneracies are divisors inside of the previous locus. So for example, the 4-sheeted locus is codimension 1 inside of the 2-sheeted locus. Yeah. Okay. Any other questions about the statement? Okay. So let me start by giving some description. So I'm going to start by just giving some description in terms of gluing, which I'll use to sort of rephrase things. So start with this description. With quotient sections. And sort of the point here is this result. It was proved by quotient Raleigh and characteristic 0. And as with many results in this talk and characteristic P, it was in thesis by Paul Levy. And this says that for any regular nilpotent, so I will denote the regular nilpotents in P, which are just nilpotents in G intersect with P reg. There exists a section of this map from P reg to the GIT quotient, whose image at 0 is E. So sort of there's enough sections to hit every nilpotent element. And the point here then is one can use the GM action to kind of reduce to the nilpotent cone. So this is sort of analogous to an argument of Jingren Chi. So analogous, probably spelled that wrong. It's like this. Anyway, to so an argument of Jingren Chi, which says will give us that if I choose some sections, so I'm going to use notation a little bit. These are going to denote kind of the image of these sections in P reg. So these will be the images of sections. So through each regular nilpotent H orbit, then the entire locus P reg is the union over the H orbits of these SIs. So kind of the costant sections are enough to generate the entire P reg, and in particular, if I take H orbits, I get a representation of this, or a description of this, this regular quotient as taking all of these costant sections over each of the i's, and then gluing by H conjugacy. So on any fiber, if two sections become conjugate, I glue them together. So for example, in the regular semi-simple locus, I will glue all of these together. There's any two regular semi-simple elements in a fiber will be conjugate. So this gives me some first description where we start to see our sheets pop up. And particularly a nice place, so maybe a remark, is that if the number of nilpotent H orbits in P is 2, then this is then this description is easy to describe. Exactly, sort of for the reasons that the questions got to earlier, which is that if I have just two sheets, then I just have to say where do they glue. I don't have to say which different elements degenerate to what. If there's one sheet, I would glue them. If there's two sheets, I just don't glue them. And the miracle of symmetric spaces is this result first due to Sakaguchi in characteristic 0, and due to Levy again in characteristic P, which says that for any simple symmetric pair, except the one that I mentioned before, which I would probably drop the involution from as I go forward, probably just denote it like this. The number of nilpotent K orbits, kind of the worst it can get, is at most 2. And in fact, you don't just say it's at most 2, there's a table. And this is kind of why I'm ruling out this for the purpose of this talk, is this one has 4, so it does involve a little bit more work. Okay. So one can reduce to this case.
So here you're considering K orbits, but in general you want H orbits, right? Or
That's right. But H contains K at least, so the nilpotent the number of nilpotent orbits can only go down from there. Yeah, so that kind of gives like a little upper bound on the number of orbits that are allowed. Right. Cool. So I guess I can reduce, so reduction to the simple case. I just want to give you the statement of kind of this reduction, which is that for any simple symmetric pair, G theta H, there exists some isogeny of symmetric pairs, which goes from sort of this abelian part. This component of the center is fixed under theta, and sort of has H given by this intersection. And then I have a bunch of non-abelian parts, Gj, theta j, hj, mapping to my original symmetric pair. This isogeny means that it's kind of an isogeny of the groups, which preserves theta, and so that the pre-image of the H is the product of the H's on the left-hand side.
This
Yep.
is for any symmetric pair, right? Not any.
Oh, so not any simple. Sorry. Thank you. Yeah. Not simple. The whole point is this is not simple. Yes. Sorry. So for any symmetric pair, it's not wrong if I say simple. There's an isogeny of this form. That's right. Such that, and sort of the point here is that these triples GJ, theta J, HJ are either simple themselves or diagonal. So either GJ is simple, or we're back into example 1 from before, where this splits as a product of two things. The point is, in the diagonal case, the regular quotient is just the GIT quotient, because we're back in that case where this is a gerb. And in the simple case, we're reduced down to the problem that we're now kind of on our way towards. And so I should say, and kind of the regular quotients, of both sides agree. So if I take the product of the regular quotients on the left-hand side, I get the regular quotient on the right.
By the way, so
Yeah.
could you even simplify further and draw an isogeny to simply connect it, like
In fact, not only can you sort of need to in order to make that lemma work. That's right. So this doesn't work for like any isogeny of groups, and so sort of the idea is you should pass the simply connected covers of each of the GJs. So really we do sort of work in the simply connected simple case. But this doesn't simplify a whole lot from there. So right. Okay. Any other questions or? Okay. So I just want to present kind of some codimension 1 simplification. It also gives you some alternate way of looking at this regular quotient, which is that if I consider this map from P reg down to this GIT quotient, or sorry, by H, and consider the constant group scheme given by the normalizer. So this is by definition, I'm going to take the normalizer of K, constant group scheme over the GIT portion. Then this constant group scheme acts on the fibers of P reg. And moreover, a result of Levy says that this action is transitive on the nilpotent cone. So again, I guess again, I'll cite Levy for this, but this is done by Cosmos and characteristic 0 at first. All right, let me say this. The NG action, okay, on this nilpotent cone is transitive. Oh, sorry. Yes.
On H orbits.
So it. Oh, sorry. No, but it's transitive here.
sorry.
So yes, you're good. It's also true on the H orbits. You're good. Yeah, exactly. So here I care about the H orbits, right? So this is a transitive action. So in particular, this thing is transitive on fibers, since this thing is kind of a gluing over sheets indexed by the nilpotent cone. And so if I choose kappa to be some constant section, the P reg, a constant Raleigh section. So I choose some section here. then I can trivialize this action, and I get that the P reg over P mod mod H is this ng of K constant group scheme quotient by a pullback of regular centralizers for ng of K. The point being that this is kind of the fixed points of it. And in particular, this gives me another way of looking at this regular quotient. So I'll put this underneath, that if I take this fat slash quotient by H, I get a quotient on top of just discrete or of just constant group schemes, and on bottom by a pullback of ng of K reg mod I H reg. So an alternate way of thinking about the jumps up in the non-separated structure is the jumps down in the components of this quotient of regular centralizers. So the result I want to mention, and this does have a little bit of work, we're still cleaning on it, but is this lemma, which this regular centralizer groups quotient by I H reg is affine. So is affine over this space of E reg. And the point is that if this is an affine map, the corollary is that for G theta H simple and not my one bad form, the non-separated locus happens on a divisor. So we have this fat slash quotient is equal to the gluing of two things along some divisor. Some divisor. Yes. And the point here is that this follows by an algebraic Hartog's argument. So we have kind of some bound on the codimension of the sets where the components drop here. So this is algebraic Hartog's. Okay. So kind of the reduction so far is that you take whatever symmetric pair you have, you feed it through and reduce the simple case. And in this simple case, let's assume we don't have this one bad form. And in that case, then we know that it's some gluing over the complement of the divisor. And so the question now becomes how to compute the divisor. So the last step is sort of some Levy induction. And this is what allows us to compute the divisor explicitly. And for this, I need to start introducing the restricted root system, which was just introduced in the last talk. So let me quick review that. So just a quick, I'll go quick on this. So if I fix some maximal abelian subalgebra of P, and if I fix a T containing it, which is some parton of G. So this is the same data as before. I have my maximal kind of theta split, and I have kind of some extension of this to some theta fixed torus. And I have some root system phi. So this will be the root system of G with respect to T. Then I can define this restricted root system to be the restrictions of roots in B to A. And throw away 0 if I get any zeros. So I have some natural kind of restriction map, which goes from phi, the restricted root system union 0. And in this case, we have sort of the analogous statements that we do to Lie algebra in invariant theory. The point being that I still have some Weil group. So it's called the little Weil group and literature group. So this is the Weil group associated to my restricted root system. Then I have sort of some Chevrolet restriction which gives me isomorphism on the GIP quotient with A mod WA. So the point is now I'm going to stratify this GIP quotient by the images of hyperplanes in A. And I'm going to tell you which hyperplanes give me non-separated structure and which don't. So let me sort of do that then. So let's fix O to be some WA orbit of hyperplanes. So root hyperplanes, I should say root hyperplanes in A. And I'll tell you whether their image, I'm going to tell you whether their image is in this divisor. So I'm going to construct from this a levy. So I'm going to take some H, which is an element of this orbit. So I'll take one root hyperplane. Then I'm going to take some subset of the restricted root system, which consists of roots, which vanish on H. And I can define L to be a connected levy with Lie algebra, given by taking my Cartan plus the sum over all roots in the pre-image of S or 0 of these root spaces in G. Let me put that up higher. The point here is that this levy so let me state this dilemma. So L, or let me first say L is theta stable. And this pair, L theta together with HL, which is the intersection of H with L, is a symmetric pair. So note this includes the claim that HL kind of, when I take the intersection, still lies between K and the normalizer group. So this is one of two places where you see this inductive kind of step happening there, and also the kind of isogeny down to simple the algebras. Okay, so the point then is that I have a comparison map. Phi, which goes from a quotient, the Weil group for L, which is a subgroup of the Weil group for A. And the comparison theorem here that allows us to function is that there is, so let me say on the unramified locus of phi, we have an isomorphism from the fat slash quotient for H pulled back along this map. With the with the fat slash quotient for L. So note this map is not everywhere defined. This is only defined on kind of the unramified locus of this comparison map on the basis. And the this map is unramified sort of exactly on the locus, which is the complement of all the other hyperplane orbits. So maybe instead of state that precisely, let me kind of say some corollary here, which is that if I want to consider the number of sheets of my non-separated cover over this particular hyperplane orbit, so over the image of this inside of A mod WA, then I just need to look at the nilpotent cone of my PL. So the number of sheets in the non-separated, so in the regular quotient, over the image of O inside of A mod WA is the number of nilpotent orbits of PL, regular nilpotent orbits of PL, full stop. So you kind of reduce yourself down to levies where you have some classification results that just tell you sort of how many nilpotent orbits there are. So let me do this in an example now. So let me put this up. Let me go back to this example of the GLN cross GLN and GL2N case. So in this case, the root system that you get by R is type C, type Cn. It's going to have two different WA orbits of root hyperplanes. So it has two WA orbits of hyperplanes. And so what are these two orbits? I get one type, so associated to sort of the short root. So if I look at the WA orbit hyperplanes corresponding to the short root, I get the Lie algebra looking like something like this, up to conjugacy, where these are sort of unknowns, and then I have some torus part. So this is sort of a non-standard torus. And in particular, I get my Levy isomorphic to GL2 cross a torus. And the GL2 action on this piece exactly gives me sort of the involution which corresponds to the smaller case of this where n equals 1. So this is GM cross GM in GL2 form. In particular, if you believe me that the HL for this is given by KL, then we've already kind of computed by looking at the hyperbolic action that there are 2 nilpotent orbits in this case. So this has two regular nilpotent orbits. So these short roots give you some non-separated structure over them. I'm going to do this down here so it's all in one kind of one board. I'll come back to this in a second. And I have sort of the second one gives me the orbit for the long root. I get some the algebra, which again, up to come to see is going to look like some A, B, A, together with some torus part, smaller rank. So, sorry, delta, beta. And sort of the point here is that these A's and B's are now 2 by 2 matrices. And the levy I get, roughly by taking A and B to A plus B and A minus B, is actually going to look like a product of GL2 cross GL2. Cross a torus, where this theta action on the GL2 cross GL2 is by swapping factors. So again, this gives me my diagonal case. So in this case, my number of nilpotent regular nilpotent orbits is just 1. I get no non-separated structure on these kind of hyperplanes. And I just want to mention for those of you that are familiar with the spectral story right away, let me kind of say that these sorts of hyperplanes correspond to ramification in the spectral curve, which carries some sort of even behavior that looks like crossing the 0 section. So this is my spectral curve picture. So this is my 0 section here. Whereas these with the long root correspond to having ramification, which kind of mirrors on both sides, and you can kind of feel the swapping factor here. This is again. Okay. Do I still 40 or? Okay, cool. Okay, great. Okay, so great. I've got a little time to also now say the consequences. So this is kind of how, in general, one computes these regular quotients. In this case, you can kind of break it down into these smaller pictures and compute the regular nilpotent orbits for some semi-simple rank 1 levies. And then there's this other story of if I have sort of some regular centralizers. So let me maybe title this section the regular centralizers. And for this section, now let me assume. So now I'm going to assume that there's a bunch of equivalent conditions here, but I'm going to assume that that my I reg H is abelian. This is also equivalent to P reg being inside of G reg. So this is this condition from earlier. This is what's known as quasi-split. So, and the reason I'm going to assume this for now is that if this is abelian, then it descends. Then I reg H over its P reg descends to some j, depending on h, of course, living over this GIT quotient. And what I want to do is say that, so the structure of these sorts of arguments to describe regular centralizers is usually to try and give some cover of this GIT quotient, some flat cover, so that I can describe my J as some V restriction of some torus. So given a let me just use nice for a second, nice flat cover of this GIT quotient, we can get a description of J that looks a little bit like J is given by some Bay restriction from whatever flat cover it is down to this GIT quotient of some torus. When we're in this sort of abelian case. Of course, often we take some invariance by some group as well. So I'm just going to leave it sort of vague at the moment. I want to give you some examples of this sort of thing. I'm really just going to give you maybe one background example and then maybe a spectral case. Due to time, yeah.
Is the bulk restriction P over H? Or K?
Yeah, so sorry, I'm a bit sloppy. They're all the same. If I take any extension from K to normalizer, the GIT quotients actually don't change. So sometimes I get sloppy and write K everywhere. I should morally H. Okay, so one example of this sort of phenomenon is in this well, I shouldn't use this example, I should take this as a result. So again, in this quasi-split situation, if I consider this flat cover of A mapping to this GIT quotient, and I'm sorry for post-stating this, but this is not our result. This is a result of Spencer. I'm sort of then this J, or at least the same argument should prove this. That this J maps to some Bay restriction of A to A mod WA of some torus C with the WA action. And what is the C? The C is kind of like the +1 part of a torus which extends A. So sort of the idea is if I have T extending A, where this is maximal theta split, then T has an almost direct decomposition to C times A, where C is some torus kind of in the fixed part. And this map is kind of some open and closed map, and the difference is only in pi naught and can be computed. So we have some analogous statement to this using parabolic covers for H. But I'm going to present right now sort of a spectral cover, sort of reduces the size of this thing. You should think of this analogous to cameral covers. And what I'm about to write is the spectral analog of that. So the spectral, so let's take this as a proposition or something. So this is, so maybe spectral covers. So spectral cover, which is that if I take so now I'm going to restrict, sorry, so let me say this. So I'm going to restrict to this example of GLN cross GLN inside of GL2N. So this is in this particular form, there is a spectral cover spectral cover of A mod WA, I'm going to denote it S. And this is just the GL2N spectral cover. So, this is the GL2N spectral cover. So it's a 2N cover over A mod W. I'm just restricting it to this sort of invariance. And this thing comes with some involution on it, induced by the involution theta. And sort of the point then is that I have a Weil restriction description of J as a Weil restriction from this quotient of the spectral curve by I down to A mod WA of GM.
Sorry, are you viewing this quotient as inside the quotient for GL2 and then pulling back? So
The quotient or the
just the S?
Yeah.
You're getting,
so this S I'm thinking about as I have some sort of spectral cover for GL2N over kind of T mod W.
Yeah.
And in the quasi-split situation, this A mod WA embeds in here, and I want to pull back that. So this is my S. Yeah. Just think about it as restricting kind of. Yeah. And sort of the last, so sort of the consequence of this for Hitchin fibers is that we can describe them in this case quite nicely, sort of as in the GLN case. So the consequence. So for Hitchin fibers. So bear with me for a second because I've got to introduce a little bit of notation on what sort of objects here I have. So I'm going to denote M reg to be the maps from a curve X. Apologize. Maybe okay. Let me write this down. Let me write what curve X is. So to P, it's by the quotient. I'll explain this notation in a second. Sorry. So I should have fixed here X to be a smooth projective curve. And P is going to be some line bundle on it. An X with sufficiently large degree. Then I have this this regular part, which sorry, I'm going to put the reg there. So this reg means that I'm going to land inside of the regular locus of the stack. And I have sort of my Hitchin base here, which is given by maps from my smooth curve X to the twisted GIP quotient. And then in the middle, I have this intermediate space. This reg stands for regular quotient, which is going to give me maps to this twisted regular fat slash quotient. And I get compositions in each of these series. And the consequence of this description of my J the consequence of the description for my J is that this first map from M reg to A reg behaves very much like the usual Hitchin fibration. So that sort of the corollaries here. So the generic fibers, I'll be a little bit vague on this. The generic fibers of M reg to A reg are going to look like Picard stack of a quotient of a spectral cover by I. So to explain kind of what this means, this XA is going to be a base change of kind of the image down here. So I have some point in my Hitchin base A, and I pull back the spectral cover over a mod WA, and I get some spectral curve for X. So we can think about these kind of the same as like just taking the zero section of some spectral equation inside of the total space of D. And this XA inherits some involution on it from the involution on S. And these fibers are given exactly by kind of the Picard stack of this quotient. And the novel feature is that if I look at the map from a reg to A, this gives me extra components. So gives extra components. Sort of the picture is that
Is A like an affine space?
so A is an affine space.
Like
Yeah. So it's just A to the n for any, as long as P is good for G, we have this kind of pretty general result by Levy. Yeah. Right. So you think about this really is like, you know, so I'm like looking at my affine space, and I have sort of these hyperplanes on which I have some sort of like, you know, non-separated structure. And whatever my point is down here, if I look at the image, if I draw the image of A of X in here, you know, something like this, then every time it crosses this divisor, I have to choose a lift into one of these two non-separated hyperplanes. So I have a choice of two different lifts. So the result is, let me kind of collect this. Maybe I'll leave this up. I'll put it right here. So the result is that generic fibers of this composite M reg to A are sort of some disjoint union of stacks of this spectral curve. But this disjoint union is going to be over sort of 2 to the power of the intersections of AX with my non-separated divisor. And in this case, this has a particularly nice description. The non-separated divisor was exactly kind of the zero section. So this this whole thing is the same as just 2 to the number of intersections between kind of XA and sort of the zero section. Zero section for XA of these Picard stacks. And I think this is where I'll leave it. So I just want to say one thing before I end, which is that this result recovers earlier work, which is due to Schapostnik. So she used spectral covers to kind of describe these sort of Hitchin fibrations in her thesis. So let me say that. This recovers a result of Schapostnik. So in the spectral case, we get some earlier constructions. Okay. So.
Is there any question or comment?
I have a comment. At the beginning of your talk, you thank Anna Peon, who unfortunately cannot come to the conference. You have to cancel. So I think it's relevant to say that the study of the Hitchin system for symmetric pairs was initiated in their thesis.
That's right.
In 2013, right? And a special emphasis, I mean, from this very point of view, and special emphasis in the Quasisplit case where a paper appear some years later. Perhaps you can,
Mhm.
I mean, besides the fact that you work in
Mhm.
characteristic P, good characteristic, and you obtain more refined information, perhaps you can comment on what is that was achieved there that you have
Yes,
improved
absolutely.
something.
And I apologize, I meant to mention this, but I seem to have forgotten. The existence of this non-separated space was actually first noted in her thesis, which is that so we have kind of this picture of this stack. Let me just take K for a second. And you have this kind of non-separated space. And so she noted that this thing exists. So the new thing here is really the description of this. So my understanding is that she actually studied these things a bit from a different perspective, working with like the normalizer group instead of the centralizers in H or in centralizers in K. Sorry, I'm getting shake. Not right on that part.
Read the paper and Oscar more recently.
Okay.
So they look at the centralizers for various different groups.
Mhm.
So they point out that there is some non-separated structure
That's right.
quotient, but it's found in examples, but it is not described explicitly.
Right.
And
Right.
then the regular centralizers in that are described in the quasi-split case over the regular semi-simple locus. And the second description is given in the NGK case as the fixed points of the Denagi-Gatescree description of regular centralizers. Then this description was improved, I think, by Levy in the case where the group is the fixed points, but we're pretty sure that Leslie Spencer's proof would generalize to other groups H as well.
Yeah. Yeah.
Any other question or?
Yes,
Yeah.
so now you have this Hitchin Fibration. What do you want? You want to support theorem? You want to? So there is a fundamental lemma.
Yeah, so there are a few different directions on this, right? One of which Benedict will discuss on Thursday with some sorts of mere symmetry questions for these things. And you may remember from Halvol's talk yesterday that there's that these things are sources of BAA branes. So there's some projected Fourier-Mukai duality between this and something on the other side, some BB brane on the other side. Another kind of question that these things are open to is, right, we expect that there should be some analog of the support theorem in this case that should be related to the relative trace formulas, some infinitesimal version of this. And I also want to note that this modular space of Higgs bundles for this kind of setting, there's a non-abelian Hodge correspondence, which tells you that there's some diffeomorphism of this sort of space over C. Now I'm fixing over C. There's a diffeomorphism of this with the character variety for the real representation. So representation of the fundamental group into G of R. So this is another kind of motivation to study this sorts of things. Yeah. So there's kind of it sits at an intersection of a few different things. I definitely say support theorems would be very nice in this case.
Do you have a guess on the support of the?
Not right now. Maybe. Maybe Spencer will say more soon. That's right.
Any other question or comment? If not, let's agree.